Welcome back to Applied Mathematics. In this video, I want to talk about the coordinate plane. I expect that you've already dealt with the coordinate plane to at least some degree in a previous mathematics course. You are aware that the coordinate plane, sometimes called the rectangular plane, sometimes called the Cartesian plane, named after the French philosopher René Descartes, has a horizontal axis, which is almost always going to be the x-axis, the vertical axis, which is almost always called the y-axis. Some other vocabulary that hopefully you are familiar with, but it may have been a while since you've thought about it previously. The point where the x and y axes cross each other is called the origin, and it has coordinates 0, 0. Remember, in general, that coordinates are written as ordered pairs. We call them ordered pairs because specifically they are always in the order of an x-coordinate followed by a y-coordinate. So if you have the point (3, 2), that always is going to be the point where x is equal to 3 and y is equal to 2. If you have instead the point 2, 3, that would be the point where x is equal to 2 and y is equal to 3. All right. Some other vocabulary that you may or may not have come across previously. The x-axis and the y-axis divide the coordinate plane into 4 regions, which we call quadrants, right? For 4 of them. We always start at the top right. This is quadrant 1. And the reason that this gets the special billing as quadrant 1 is because very often it's the only one you use. If you are collecting data on how far a ball rolls down a hill over a given period of time, you're going to start with the time 0 and the ball at position 0. The ball is going to travel some distance, which is going to be some positive number. It's going to take some amount of time, which is also going to be some positive number. So all of your data appears in quadrant 1, and you leave the rest of it off. From there, we proceed using what's called the right-hand rule. To understand the right-hand rule, take your right hand, and for me this kind of looks like my left hand, doesn't it? I'm in a mirror. I have to do this really strangely, but that's okay. Take your right hand. This is my left hand. It looks like a right hand. Put your right hand on the origin so that your thumb is sticking up. Your fingers naturally want to curl in this order, and that's the order we follow as we name the other quadrants 2, 3, and 4. The right-hand rule has a number of implications in the understanding of graphing, generally the branch of mathematics called analytic geometry. And so this is just one place where it shows up. If you continue onward in your study of mathematics, you'll see it in a number of other places. All right, but quadrant 2 over here, let's just take some random point. -4, 1. You'll notice the x-coordinate is negative, the y-coordinate is positive. In quadrant 3, I don't have a lot of space over here, so let's just grab this point. -1, 1, where both x and y are negative. And then quadrant 4 I have completely filled up. I don't have any space to put a point in there, but maybe something like 2, -5, which has a positive x-coordinate and a negative y-coordinate. Points that are on the axes, like the point here, 4, 0. 4, 0 is not in the first quadrant. It is also not in the fourth quadrant. points that are on the axes are not in any quadrant. They're the special cases. That's the reason that very often those things become important in their own right. All right, let's get my head out of the way and let's look at a couple of practical applications. I mentioned the idea of scatterplot, although I don't think I used the name of it, as a reason we might care about just the first quadrant. And so I can sketch out some coordinate axes. I'm going to draw this really exaggeratedly large in the first quadrant and tiny in the other quadrants, because again, the only thing I care about is fitting my data onto the picture. So I've got some axis over here, which I'll use for time, and some other axis that I'll use for distance. I'll label it as t and d instead of x and y, but it works just the same. I'm writing this on something that's supposedly graph paper, but I know that sometimes it's a little bit hard to actually see that. So let me put a couple of tick marks going across here. It is important that you put in tick marks. It's important that the numbers are equally spaced in your tick marks. But some of the things I want you to notice on this graph are my scale is not equal. Notice over here, I've got a large space between each tick mark, and every other tick mark is labeled as 1, 2, and 3. On the vertical scale, my tick marks are much closer together. My third tick mark is labeled as 3, so I can fill in and say, oh, this must be 1, 2, 3, 4, 5, 6, and so on. So my scales are different. There are some times when that's perfectly fine, and there are some times when that will give you a very misleading idea of what's going on. Always think about what that means in the practical application you're looking at. Right here, I'm looking at time and distance. I didn't write units in because I'm lazy, but time is probably measured in seconds or possibly minutes or even hours or days. Distance is probably measured in inches or centimeters or maybe meters or even possibly kilometers or yards or, Regardless, the important thing here is that the unit of measure is different. A space of 1 second has absolutely no relationship whatsoever to a space of 1 centimeter. So because of that, I'm not worried about the fact that my scales are not related. If I was using the same kind of unit, I would be much more concerned. All right, but let's go ahead and plot this data. When time is 0, distance is 0. When time is 0.5, distance is 1. When time is 1, distance is 3. When time is 1.5, distance is 6. When time is 2.0, the distance is 9. The thing that jumps out to me immediately in this picture is that this is not a straight line. If I try to draw a straight line through the first 2 points, it wildly misses the rest of the graph. If I try to draw a straight line through the next 2 points, it wildly misses the rest of the graph. If I try to draw a straight line through the last couple of points, you'll see that there are 3 points that fall in a straight line, but it definitely misses the rest of the graph. And so, trying to draw in a curve connecting the points in a scatter plot may or may not be something that's reasonable to do. I did not mean for myself to show up above there. I hit the wrong button. Sorry about that. I just wanted to get rid of those dots. All right. The biggest use we're going to get out of the coordinate plane in this course, which I'll be perfectly honest, is likely not the biggest use you'll get out of the coordinate plane in other courses, unless you're continuing onward in mathematics. But our biggest point here is going to be graphing an equation in two variables. For example, let's take a look at 2x plus 3y equals 12. One of the tools that I use for graphing, and hopefully you know more sophisticated tools for dealing with this particular equation, but I can set up a table. I can pick a value for one of these variables, plug it in, and see what happens. If I pick that x is equal to 0, then I will have 0 plus 3y equals 12, which is just 3y equals 12, and dividing by 3 gives me that y is equal to 4. So 0, 4 is a point on this graph. If I pick a different value for x, maybe I'll pick x is 3. Right? Well, then I'll have 2 times 3 plus 3y equals 12. That's 6 plus 3y equals 12. 3y then must be equal to 6, and y itself is going to be equal to 2. So I've got another point on the graph, 3, 2. And I don't know, one more? What if I plug in x equals 6? Well, when I try that, I get out y equals 0. All right, so there's a third point. If I wanted to, I could try a couple more points, but I'm instead going to use what I know. I'm running out of space and I want to still have this, so I'm going to just select that and copy it down below. You are working on a piece of paper where presumably you can still see that as you look down to some clear space. But regardless, I'm going to sketch out some coordinate axes. And even though the points that I chose are all in the first quadrant, x and y are positive in all of those points, I know that that's not necessarily going to be the case. So I'm drawing this nice and big with the origin centered so that I have plenty of space to work around that. Again, I'm setting up my x and y axes. I'm labeling them as x and y. I'm putting in some tick marks and I'm labeling the tick marks. Not every tick mark, but enough of them. In this case, I don't have the context to say for certain that my horizontal and vertical axes don't need to have the same scale, so I'm going to err on the side of caution and use the same scale. On my graph paper, this is 2 blocks to get to 1, another 2 blocks to get to 2, another 2 blocks to get to 3. 2 blocks to get to 1, another 2 blocks to get to 2, another 2 blocks to get to 3. And I've labeled every other point just so that my numbers aren't too much in the way. From here, I'll go ahead and plot my points. When x is 0, y is 4. That's this point. When x is 3, y is 2. And when x is 6, y is 0. That gives me a couple of points of interest. From here, I'm taking information that I have outside of just this. And I know that the equation that I'm graphing is what's known as a linear equation. It has x and y, neither of them raised to any sort of a power. So I know that I will be able to predict that the graph of this equation is a straight line. Using that information, coming down here to where I just drew my graph, and let's try that again. That looks a little bit better. If you squint and tilt your head, that looks like a straight line. Right. One of the interesting things that I want to stress in this course is that unless you have reason to suspect otherwise, and we'll get into reason to suspect otherwise in a little bit, we're going to assume that graphs continue indefinitely, and we want to indicate that by putting arrowheads on the graph. Right? The graph does not stop where the points you chose to plot stops. My graph goes through these points and keeps going down this way. My graph goes through these points and keeps going up that way, where my hand gets cut off because I ran out of green screen. I want to make sure that my graph indicates that. Like I said, a little bit later on, we're going to look at some equations where that doesn't quite happen, where you do hit a stopping point. But for this particular graph, it keeps going, and we need to represent that appropriately by using these arrowheads. I think that that's probably a good place to wrap up on this video. So as always, thank you for joining me, and I'll see you next time.